Hi guys, welcome to Programmers Week. Before starting the presentation, I would like to tell you and encourage you to address your questions in the chat section, and I will answer to them when I'm done presenting. Also, because I'm a little bit of paranoid, if a power outage happens, I have a backup, so within 5 minutes I will reconnect, so please wait for me if that happens. Now we should begin. I'd like to introduce myself. I'm a regular person who loves comic books, dogs, and Linux, normal. After I graduated, I worked as an ETL developer, so a lot of databases and SQL servers. I started being interested about the web world, and I've been working as a front-end developer for 4 years now. Oh, the last two being a part of the Cognizant Softvision team. I think this is where I started being comfortable or more comfortable with the presenting, and I thought it's a great opportunity to talk to you about a really cool subject, the sound of data. So in 2018, I participated to a conference in the USA called Python. It's a conference about Python, but not just Python. And I attended one talk that really opened my ears, not eyes, opened my ears and made me very curious about this subject of representing data through sound. In order for us to understand what we are going to discuss about today, we need to make sure we know some basic concepts. I know that everybody knows about them, but we need to focus on certain particularities. What is sound? Well, sound is just a form of energy that produces the sensation of hearing. We can also say that it comes from vibrations, and those vibrations create sound waves, which the waves move through environments such as air and water before reaching our ears. All sounds are just pure combinations of pure frequencies, and it has every sound has 4 main characteristics. The first one is loudness. This is the degree of sensation of the sound. It depends upon amplitude, and the amplitude determines the loudness of the sound. The more the amplitude of vibration, the louder is the sound. The lesser the amplitude of vibration, the sound gets more feeble. Pitch. This is what determines the sharpness or depth of the sound. It depends upon the frequency, and more the frequency, the voice is sharper. Less the frequency, deeper the sound. Quality. This I think is my favorite, because this property is the property by which one can distinguish between 2 different sounds of the same pitch and loudness. For example, in a dark room where there is no light, of course, it's dark, and let's say we have 10 people present there. We can easily recognize the sound of our friend's voice among all the people due to the unique quality of their voice. Intensity. This is a hard one. I would say it's defined as the number of sound waves passing 1 meter square area in 1 second. So how many sound waves are passing 1 meter in 1 second? This depends, of course, on the square of amplitude, and we know that sound can travel through all 3 states, solids, liquids, gases, and the speed of the sound depends upon the density of the environment. The speed of sound is maximum in solids, and listing gases because the particles are closer in solids. As a real life example, just think about when it's really foggy outside. You can't hear as well as you could when it's clear. Now we are all sound experts, and I think we should try our luck with the data too. So although data, information, knowledge are often words that are being used as the same, each of these terms have a distinct meaning. Data is sometimes to be transformed into information when it's viewed in a certain context. We are going to treat data as a set of distinct pieces of information, usually formatted in a special way. And now, the reason why we are here, sonification. This refers to the mapping. So the mapping of data values to properties of the sounds, such as pitch, volume, duration, location. It's a general term for conveying information through non-speech audio. It's pretty similar to how the term visualization expresses the concept of conveying information or data graphically. For example, alert sounds for events such as receiving new email or program errors are just simple forms of sonification, commonly being used in user interfaces for computers and other devices like our phones or laptops. The sound of data or data sonification. This refers to using sound to represent data and is usually intended to either complement or replace the traditional visualization. Data sonification is just structured data converted to sound. Although it has existed since quite a few times, it's not known exactly when it has been first used. It has not been explored as much as visualizations, and in my opinion, it makes it an excellent choice for people who want to try something new, cool, and that's going to make a little revolution in our industry. I want to point out that it's really important to make the distinction between music and sound, and data sonification isn't making music. It's simply the auditory equivalent of data visualization. So it's not music. Sorry to disappoint if you thought we are going to have a little concert, but who knows, maybe later. Well, the why. It's really important to know why we should be interested in this subject. The purpose of exploring data sonification is to try to make science available for everyone, regardless of the lack of sight. It's also important to communicate aspects of complex information in a clear and efficient way. And it helps supporting specific analysis of aspects of the data. And maybe the most important, it shows us patterns and relationship in the data, within the data. So even though we don't hear very often about the subject, there are a lot of people who use data sonification. And one of them, no, it's not me specifically, but is Rita Singh. She's a scientist whose expertise includes speech recognition, audio signal processing, and pattern recognition. And in order for us to understand better how awesome she is, I'm going to tell you a short but real story. In America, there are a lot of people who used to call 911 and report fake major incidents. The Coast Guard gets a lot of fake maydays, calls over radio. Those maydays calls are calls that mean that people's lives are in danger. When they get these calls, They launch searching missions, they send boats, helicopters, specially trained people, and of course they search hundreds or even thousands of square miles at sea. Not only it's really expensive, but it's really dangerous. In 2014, so 6 years ago, there was a joker caller who kept making calls over several months. And the worst part is that the police officers, some police officers died after being part of the rescue missions. The authorities, of course, they tried their best and tried a lot of approaches to catch the pranker, but nothing really worked until Rita stepped in. After she and her team analyzed the calls, they studied the voice of the caller, and she was able to make a full profile of that picture. So remember, the whole profile was built from the information that the voice gave them. It was a male who was brought up in America. He wasn't born there. He was white, about 175 centimeters tall, 40 years old, and around 75 kilograms. He was not on a boat, as the police investigation led to at first, but he was in a warehouse of some kind, and the warehouse had many machines laying around. His equipment was homemade, most likely by himself, and he was still learning how to use it. His improvised radio room had a glass wall, and he wasn't in any kind of trouble, for example, running from the police or hiding from people who knew him. The experts were even able to determine that he was sitting on a metal chair on a concrete floor during every call he made. So those are all the informations about the profile that Rita and her team could tell about the prank caller. Of course, there are more, but that's known to the general public. Maybe you're thinking how? Well, all these were possible because of our hearing. Our hearing is well suited to identify and contrast periodic and aperiodic events. As well, we can detect small changes in the frequency. So when we hear something, we can extract complex data that might be embedded deeply within both static and noisy signals, such as the environment, let's say. I think this is a great example of data sonification because it allows researchers to stumble upon new patterns and questions when exploring their data. In this way, the data sonification performs much the same function for science experts as it does for the general public, because it helps us too. It clarifies the data's narrative and also suggests a path forward inquiry. From hearing people's voices, we make judgments all the time about a lot of aspects, such as gender, age, ethnicity, social background, state of mental health, surroundings, a lot. We do so often and easily without even realizing. When we talk on the phone, for example, we make assumption if that person is sad or happy or tired. And the information in our voice is in the micro features, and the artificial intelligence is used to discover the information, extract those features, measure it, learn from it, of course, and then predict from it. In the previous example, we could see a profile for the pranker caller. For profiling, the scientists compute humans' judgments. They make machines do what we already do, but much better, by using the micro features from our voice and using the artificial intelligence. In this image, we can see, and we can't see, I'm going to tell you, it's a person saying his name, Thomas Sullivan, and we can see on the top of the voice signal, on the top of the page, there is the voice signal. And what is below is just a representation of the frequencies in his voice. That's the most important part. We can also see that the pattern in his voice change while he's talking. And the picture below, it's called a spectrogram. Here we have the pitch pulses of 3 different people saying the same word. This is the word I'm saying the most often when I'm presenting. We can see the different patterns between the people on the side and the one in the center. And that's because the person in the center has Parkinson. And the markers show up on this representation. And we can see signs of diseases like Parkinson from an early stage. And next, here, we have the spectrogram of a well-known dictator. This is part of one of his speeches from 1934. And it turns out that he already had signs of Parkinson since back then. And even though until some time ago, there was just speculation about him having Parkinson, we can now have proof that he indeed had Parkinson. Another positive example, here we have the spectrograms based on Queen Elizabeth's voice. This is a Christmas broadcast 50 years ago, and you can see the arrows. Those arrows mark the same exact words. We can see that with age, the lines have smeared and moved down. And that's one of the signs and one of the effects that happens to our voice when we age. For analyzing the sound, it's not just the voice. It's also the environment in which the voice is embedded, absorbed. For example, the reflections here in the room causes this spectrogram from which the scientists, not us, can tell that this guy was in a room with extensive glass panels. I think that's how they're called. With glass. Our voice, for example, has information about us that not even our own DNA has. And also about our surroundings. So it's really valuable. And that's why experts are working on recreating the human persona in 3D from voice alone, which I think it's both cool but scary. Moving on, we have another amazing scientist, and this is the last scientist I'm going to tell you about. Her name is Wanda Diaz-Merced. She's also known as the astronomer who hears stars. She's both an astronomer and astrophysics, and she's best known for using sonification to turn large data sets into audible sound. Since she was little, she had a dream of studying stars, but of course in the visually orientated scientific world. When she lost her sight in her 20s, her dream, of course, suffered a major setback, and due to her passions, she discovered sonification and realized that she could use her ears, not just her eyes. She found a way, and she figured a method how to detect patterns in the stellar radio data. While working at the Harvard Center, her sonification inspired a lot of musicians, and a researcher wanted to have a little project named X-Ray Hydra. And no, it's not the secret organization like you see, like the one you see in the Marvel universe, though it sounds like it. X-Ray Hydra is just an album of oddly jazzy music, and it's based on her audio representation. So if you wanted some music for this presentation, I think this is the part. Now, of course, she's advocating for a more inclusive scientific community. She thinks that science is for everyone and it has to be available to everyone because we are all natural explorers, which I totally agree. Watching one of her talks, a little quote got my attention, and it was, "If we only see with our eyes, our perception is very narrow." That leads us to our next slide, perspective. The sound of data using sound offers us a new perspective regarding the data and the problems they are to solve. Looking at topics from multiple perspectives, it offers you more details, so more knowledge about that topic. Beside the details, it makes it more accessible, so more people can be included. Moving on, as I told you earlier, the data sonification has been used for some time, and I will try to present you some checkpoints from history that mark the evolution of this. I hope it won't be boring, I promise. So around the year 350 before Christ, Aristotle was among the first to note that sound could be heard in water as well as in the air. Nearly 2000 years ago, someone else made the observation quoted above that ships could be heard at great distances underwater. The first recorded use of sonification was by Leonardo da Vinci in 1490, who used a tube inserted into water to detect vessels by ear. As you can see, this is how the experiment looks like, and the quote was, "If you cause your ship to stop and place the head of a long tube in the water, okay, and place the outer extremity to your ear, you will hear ships at a greater distance from you." So you can see in the images that the experiment is pretty simple, but it's something that was very useful for the sonification industry or domain. We can see here, those are the sketches, and no, it's not the sketch for the bells, it's for the tube. And the tube was the first recording technique of the sonar. Sound navigation ranging. So even though Leonardo da Vinci used it in 1419, his invention didn't have a name until 1918, when sonar was discovered and registered as a technique that uses sound propagation to navigate, communicate, or detect objects under the surface of the water, on or under. The acoustic frequencies used in sonar systems vary from very, very low, and those are infrasonic, to extremely high frequencies, ultrasonic. It was first used during World War I to detect submarines. Then the technology, of course, improved, and by World War II, it was used again for military purpose. In the 1960s, the development of technology made plotting of sonar data much easier, but this technology was not available to the civilian scientific community until the US Navy declassified it in 1970s. We have here the Geiger counter. It's really great. I think probably some of you have it. It's just an instrument that it's used for detecting and measuring ionizing radiation. It's known as a Geiger-Müller counter, and it's widely used in applications such as experimental physics, nuclear industry. It detects ionizing radiation such as gamma rays using the ionizing effect produced in the tube, and it's perhaps one of the world's best known radiation detection instruments. It has been very popular due to its robust sensing element and relatively low cost. For example, on Amazon, you can find it at around $300–400. So if you think about its importance, it's relatively a low cost. I will try to explain how it works. So essentially, it's just a tube that's filled with gas, and that gas has high voltage going through it. And whenever a radioactive particle, here, this is where the particle comes in contact with the gas. So whenever a radioactive particle comes in contact with that gas, the gas conducts electricity, and that causes ionization. It's basically just change in the electrical and a change in the electric charge, and that's ionization. So it's detected by the Geiger counter and then emits a little click, and also it shows you here on the display. So it's really useful because you can get that feedback at the moment you need it, not after analyzing the data. Moving on, we first need to know what is an interferometer. Those are investigative tools that are used in many fields of science and engineering. They are called interferometers because they work by merging two or more sources of light in order to create an interference pattern. And they are often used to make very small measurements that are not achievable any other way. This is why they are so powerful for detecting gravitational waves. We have here LIGO, Laser Interferometer Gravitational Wave Observatory. We'll call it just LIGO, and it's the world's largest gravitational wave observatory, and it's a marvel of engineering precision. It exploits the physical properties of light and of space itself to detect and to understand the origin of gravitational waves. And it does that by compressing two enormous laser interferometers located 3,000 kilometers apart. This is how it looks like. It's unlike any other observatory on Earth. It was built to detect cosmic gravitational waves and to develop gravitational wave observations as an astronomical tool. As of December 2018, LIGO has made 11 detections of gravitational waves, and 10 of them are from binary black holes mergers. The other event was the first detection of a collision of two neutron stars, and it's a huge step in science. First, because it helps us discover more about our origins, and second, it also suggests that Einstein was right and time and space can bend, and this tool can help turning his theories into facts. So it's really cool, and you can find a lot of things about it on YouTube, for example. It's amazing. And now I'm going to play a little sound, and then I'll explain. Okay, so this was the sound of two black holes colliding 1 billion light years away from our solar system. and it was recorded by LIGO experiment. It's the first event like this. What you heard is just gravitational waves converted to audible sounds, and the faint thumb matches the frequencies of detected gravitational waves, and the louder chirp is a higher frequency better suited for our human ears. We've been through history, now we're living in the present. So right now there are a lot of techniques, but the majority of those sonification techniques are software and algorithms, which is great for us, the programmers. Even though it's not known to us, there are several domains who use sonification. For example, we have the sonification of sleep. Sleep is just a state of reduced sensory and motor activity, and there are different stages, each one with a distinct pattern of associated neurological features. And the electrical activity of the brain can be, of course, registered, and the resulting signal, it's called electrocephalogram. We are going to call it EEG. And by encoding the EEG signals to audible data, it's easier to compare and to read actually hear the data. So it's easier to work with. And there are many others, such as the sonification of lipids, which is really important now. It's used to make the most clear and effective medicines. We can see the data sonification has an important role in research. And of course, we know engineers are very creative. So next we have a translation of the structure of COVID-19. So this is music. This is a musical representation of the structure of the spike protein of COVID-19. I'm going to play some seconds and then explain it to you. As you can see, it's pretty calm. The sound you heard, maybe you heard some bells, some flutes, all represent different aspects of the spike-like protein that pokes from the virus surface, and it helps it latch onto unsuspecting cells. Like all proteins, the spike is made out of combinations of amino acids, and using sonification, some scientists from MIT assign each amino acid a unique note. And then they converted the entire protein into a musical score. Of course, in real life, these amino acids tend to stretch out into a sheet, and researchers decided to capture these features by altering the duration and volume of the notes. As you can see, also due to heat, a lot of molecular vibrations get their own sounds. And as for the instruments, they were entirely the expert's choice. The scientists decided to make music from the data, but usually that's not a common practice. I guess they just wanted to have fun, and most probably because it's something for the general public, it has to be understood or enjoyed. But why would you represent a virus through sound? This format helps finding sites on the protein in where drugs might not be able to bind, and that's possible simply by searching a specific music sequences that matches to these sites. As the researchers said, not me, it's faster and more intuitive than the conventional method used to study proteins, such as molecular modeling. They also compare the musical sequences of the spike to a large database of other sonified proteins, and it might be possible to one day they will find one sequence that can stick to the spike, and most important, preventing the virus from infecting a cell. Oops. Okay, now we have NASA MATHTRAX. It's just a tool, a way to visualize mathematics. It provides user a more concrete presentation of the concepts they are studying. And of course, it includes additional features that provide different methods of visualization. While a graphic calculator only draws graph or of an equation, this provides a text description of the graph and also an audio version of the graph. And the idea was came from Sheldon, not the one from the Big Bang Theory, but the one from NASA, an engineer who was blind. And over the years, he developed computer tools to make the information he was using more accessible to him and to others, of course. Software. Because I'm running out of time, of course, and I want some time for questions, if there will be any questions. I have here some ideas. Of course, you can find a wide range of software that's meant to help you with the sonification of the data. There are a lot of Git repositories, but also some credited or better tested softwares. And I'm going to mention some I worked with. As you can see, their names are very original. Most of them are in Python. The only one is xSonify, that's in Java. And that it's just sonification data analysis tool for displaying science data as sound. We have the Sonifizer, is a data sonification API. The sonification sandbox, it allows the user to map data to multiple auditory parameters. It's very easy to work with. We have SoniPy. This runs on Raspberry Pi B. It's the model with the speakers. xSonify, I've already told you, and SoniPy, it's a software environment for sonification research. It wraps modules for data acquisition, storage, sound rendering by encapsulating them with Python. And next we have a demo, Sonify, but this is a tool to turn your pictures into musical sound, and I'm not sure if you can hear it. This is how this picture sounds like. It's almost nothing, and I'm going to upload a new one, and you can already see the difference. Okay, perfect. You can choose here some colors if you want to hear it, and you can see that you can only hear the sound when it's aligned with the colors. I have a link in my presentation, and I will make sure you get it. Moving on, because I'm running out of time. This was my inspiration for this talk. This is a talk from Erin Bresswell from PyCon. A lot of NASA articles that are the best, in my opinion. TED Talks and this documentation, Sonification in Python. Mentions during the talk about Rita Singh, Wanda Diaz-Merced, about LIGO. I really, I would like you to read more about LIGO because I couldn't tell you everything about it. Okay, and next we have the sonification code. I don't have time to make your demo, but this this Git repository is the best. It has a lot of examples, and you can easily build your own project. If you want this presentation, you can you can write an email for pw@softvision.com. It's Programmers Week. You can find me on LinkedIn and on my email address. And thank you. And I should start answering to questions if there are any questions. I'm not sure I can see them anymore. Just a second. Okay, no, I can't. Okay, so I can see the questions, I guess, because it got interrupted. Okay, but if there are questions, I will answer to them on email. And thank you very much for being here, and sorry for the technical problems. Have a great day, and please join more Programmers Week talks. Bye.